Welcome to today's paper reading. Today's paper is titled AIOS, LLM Agent Operating System. This paper was published on the AR14 preprint by Kai Mei and colleagues from Rutgers University. The integration of large language model, LLM, based intelligent agents faces several challenges, including suboptimal scheduling and resource allocation, difficulties in maintaining context during interactions, and complexities in integrating heterogeneous agents. To address these issues, this paper introduces AIOS, an LLM agent operating system. AIOS is designed to optimize resource allocation, facilitate context switching across agents, enable concurrent execution, provide tool services, and maintain access control. The paper outlines the architecture of AIOS, its core challenges, and basic design and implementation. Experimental results demonstrate the reliability and efficiency of AIOS modules and concurrent agent execution. The project is open source, aiming to improve LLM agent performance and efficiency, and to foster the development of the AIOS ecosystem. In the realm of autonomous agents, research is focused on creating systems capable of operating independently, making decisions, and performing tasks with minimal human intervention. These agents are designed to understand instructions, process information, and take actions to achieve autonomy. The emergence of large language models, LLMs, has significantly advanced agent development. Current LLMs demonstrate remarkable capabilities in understanding instructions, reasoning, and interacting with both human users and external environments. LLM-based agents, built on these powerful models, exhibit strong task fulfillment abilities across various environments, from virtual assistants to complex systems requiring creative problem-solving and planning. Figure 1 illustrates how a travel agent, as an example of an LLM-based agent, utilizes both LLM and OS resources to accomplish a task. The agent breaks down the task of organizing a trip into manageable steps, such as booking flights, reserving hotels, processing payments, and updating calendars according to user preferences. This process showcases the agent's reasoning and decision-making capabilities, which are distinct from traditional software applications with predefined functions. The agent's interaction with both LLM services for understanding user preferences and OS services for executing software is crucial for realizing this travel scenario. The evolution of operating systems has progressed from simple batch processing to advanced multitasking systems. This evolution includes the modularization of key responsibilities such as process scheduling, memory management, and file system management. Additionally, the introduction of graphical user interfaces like Macintosh, Windows, and GNOME has made operating systems more interactive. The operating system ecosystem has expanded to include comprehensive developer tools like Android Studio, Xcode, and Cloud SDK, which facilitate efficient software development and deployment. On the other hand, large language model, LLM-based agents have been developed for complex task solving. These agents can be single-agent systems, handling tasks like travel planning and personalized recommendation, or multi-agent systems, which can be cooperative, competitive, or a mix of both. Multi-agent systems are used in applications such as role-playing, social simulation, and software development. Figure 2 provides an overview of the AIOS architecture, which is organized into three distinct layers: the application layer, the kernel layer, and the hardware layer. The application layer includes agent applications developed using the AIOS SDK, which abstracts system calls for easier development. The kernel layer is divided into the OS kernel and the LLM kernel, with the latter focusing on LLM-specific tasks like context management and agent scheduling. The hardware layer consists of physical components like CPU, GPU, and memory, managed indirectly by the LLM kernel through the OS system calls. The AIOS architecture is structured into three main layers: the application layer, the kernel layer, and the hardware layer. In the application layer, agent applications like travel agents and math agents are developed using the AIOS SDK, which provides a high-level abstraction of system calls, simplifying development. The kernel layer is divided into the OS kernel and the LLM kernel, with the latter focusing on LLM-specific tasks such as context management and agent scheduling. This layer includes several key modules designed to manage agent application execution. The hardware layer consists of physical components like CPU, GPU, and memory. The LLM kernel interacts with these components indirectly through the OS system calls, ensuring abstraction and security. The AIOS system is composed of several key modules, each designed to handle specific aspects of agent management and interaction. The agent scheduler is responsible for managing the execution of agent tasks in a concurrent manner, utilizing strategies like FIFO and round-robin to optimize processing times. This ensures that tasks from different agents are interleaved, reducing waiting times and maximizing resource use. The context manager plays a crucial role in managing the context provided to the LLM, including functions for context snapshot and restoration, which are essential for resuming interrupted generation processes. It also handles context window management to accommodate long contexts. The memory and storage managers differentiate between short-term and long-term data storage, ensuring that data is accessible only while an agent is active and that long-term data is preserved for future use, respectively. Figure 3 illustrates the agent scheduler, which manages agent requests efficiently. It shows the sequential execution paradigm where tasks from the same agent are processed first, potentially increasing waiting times. The scheduler employs strategies like FIFO and round-robin for concurrent execution, interleaving tasks from different agents to balance waiting and turnaround times, ensuring no single agent monopolizes resources. Figure 4 illustrates the context snapshot and restoration process using beam search with a beam width of 1. This process is crucial for managing the state of the LLM's generation when agent requests are suspended by the scheduler. The example agent request involves determining the weather at the destination of flight UA057. The LLM evaluates multiple potential candidates at each step, preserving the most promising paths for further expansion based on the predefined beam width. Figure 5 illustrates the management of interaction history using both Memory Manager and Storage Manager. The Memory Manager is responsible for short-term data storage during the active lifecycle of an agent, ensuring rapid data retrieval and processing. In contrast, the Storage Manager oversees the long-term preservation of data, managing information that needs to be retained beyond the agent's active lifespan. The interaction history is stored in various formats including local files, databases, and cloud storage, each serving different purposes in the data management process. Table 1 provides an overview of the managed tools within the AIOS system. These tools are categorized into 4 main areas: search, computation, database query, and image processing. Each tool is described with its function and the required input and output format, which can be either image/text or text. The tools originate from various sources such as Google, Bing, Wolfram Alpha, SQL databases, Wikipedia, Arxiv, and more, covering a wide range of functionalities to enhance the capabilities of the AIOS system. Table 2 provides a detailed list of LLM system calls, categorizing them into agent management, context handling, and memory and storage operations. Each call is described with its name, brief description, and arguments, offering a comprehensive view of the basic functions available within the LLM kernel. This table serves as a reference for understanding the foundational operations that support complex agent requests in the AIOS ecosystem. Table 3 provides a comprehensive list of SDK functions available in the AIOS SDK. These functions are essential for managing agent lifecycles, resource monitoring, and complex operations within the AIOS framework. Key functions include initialize agent, which sets up the environment for agent execution, and generate plan, which creates a plan for an agent task. Additionally, functions like authenticate agent and monitor resource usage ensure security and efficient resource management. This table is a crucial reference for developers looking to harness the full potential of their agent applications within AIOS. In this section, we evaluate the correctness and performance of AIOS modules with multiple agents running in parallel. We focus on 2 main aspects: consistency and performance. For consistency, we use BLEU and BERT scores to compare the outputs of multi-agent and single-agent configurations. The results show perfect alignment with scores of 1.0 for both metrics. This indicates that our design effectively supports concurrent multi-agent operations. For performance, we compare AIOS with FIFO scheduling against a non-scheduled approach using waiting time and turnaround time as metrics. The results show that AIOS scheduling significantly improves both waiting and turnaround times, especially for later agent requests. This highlights the importance of our scheduling mechanism in managing parallel operations of multiple agents. Table 4 illustrates the consistency of LLM-generated responses when multiple agents run in parallel versus when a single agent runs sequentially. The table shows that both Biliu and BERT scores reach 1.0 for all agents, math, narrative, rec, across different LLM backbones, Gemma 2 be it, Gemma 7 be it, Llama 2-13 be Chat HF. This indicates a perfect match between outputs in multi-agent and single-agent contexts, confirming the design's effectiveness and supporting concurrent multi-agent operations. Table 5 illustrates the effectiveness of agent scheduling in comparison to non-scheduled sequential execution. Key metrics include waiting time and turnaround time for different agents under various LLM backbones. The sequential approach shows significant delays for agents later in the sequence, while the concurrent execution with scheduling demonstrates more balanced and efficient performance across all agents. The AIOS architecture proposed in this paper is designed to support the development and deployment of large language model-based agents. It aims to create a more integrated, effective, and efficient ecosystem for AI agents. The paper contributes valuable insights and methodologies to both AI and system research, providing a practical solution to the integration issues faced by the diverse AI agent landscape. Looking ahead, future research can build on this foundation to further refine and expand the AIOS architecture, ensuring it continues to meet the growing needs of developing and deploying LLM agents. The future research directions for AIOS include the development of advanced scheduling algorithms. These algorithms will focus on analyzing dependencies among agent requests and optimizing computational resource allocation. Additionally, the integration of locally deployed models into the scheduling framework will be explored, including the management of tool status and snapshots. In the area of context management, more efficient mechanisms will be devised to enhance user experience, such as time-efficient context management techniques and context compression prior to snapshotting. For memory and storage architecture, a shared approach will be adopted, enabling agents to access a communal pool of resources. This will improve decision-making abilities and explore hierarchical storage solutions to optimize data retrieval and storage efficiency. Thank you for watching.